Thank you very much for the
Yeah.
kind invitation. And yeah, hello, everyone from my side. So I was asked to start and then bring these two questions that I hope can also bring insights into your Cinderella project and also any other project you are involved in. So the how, the why and the how of XAI for medical imaging. So here I want to start with some of the critical examples. So what you see on the very left is a paradigm called shortcut learning. So shortcut learning is, in easy words, is the model is learning, is performing, but is picking on spurious correlation, is using some biases that might exist in that data, and is basically solving the problem in a different way. Typically, that different way leads to problems of generalization or the model just being quite brittle. So what you see on the left, for example, I like to show here on the right, I'm in Switzerland, so we have a lot of green and background here, where those cows were classified actually by the background. So you can see here at the bottom, these are examples where the machine could not recognize the object. So here's it's a cow at the beach. And then the system just failed. Similarly, here you see this yellow track where probably you won't see the difference between those two images at the top, at the bottom. There is some adversarial attacks applied. These are very nuanced perturbations applied on the image. And the system again failed. We know by now that systems can see higher frequencies than our visual cortex can, and therefore those are frequencies that probably the system is using, but are leading to then generalization issues. Then on the right, you see some examples in medicine. This is one of those multiple COVID papers we saw in the last years, where here the idea was to show that shortcuts also exist in medical imaging, and you see areas where the model were looking at. So these are the so-called saliency maps, showing us that the model sometimes doesn't even look at the area of importance as a human would do. So this was a kind of a mini bomb in the community. This was a Lancet paper where it was shown that AI models could recognize race, without actually, these models were not explicitly trained to do that, but they had features that were able to recognize race to a good accuracy level. So here they use, researchers in this study, they use explainable AI, again, saliency maps, where they were then showing, these are the areas, this heat map shows pixels that are important for that task. Then they would, as you see on the right, those pixels would be ablated, they would be blacked out, and then you would see how the accuracy would plummet. This is kind of worrisome. This also leads to those questions about fairness, again, biases and spurious correlations being picked up by a model. So this was one of those messages that in my career kind of scare me. A system that is actually performing by the metric might be good and deployable, but might not be that might be working under different conditions. What you see here is something we've been working for many years. We have an FDA-approved systems on the problem of segmenting glioblastomas. So we were working back, you can see in 2018, on classifying what is called a low-grade and a high-grade gliomas. Patients with a low grade can live for many years, whereas patients with a high grade have a very few months of average survival. So out of curiosity, I remember back in the days, explainable AI was not really a thing in medical yet. And discussions with the colleagues, we said, why don't we provide or here compute those in saliency maps? And we saw something, a pattern that repeatedly would look like this. So you can see those red spots that I'm highlighting here were used by the model to classify a high grade or a low grade. And you can see that the lesion, that the tumor is actually over here. So what happened is that we were introducing a very sharp edge due to our pre-processing, and the model started picking on those sharp edges, those high gradients, and to solve the task. And then we realized that the model was in a kind of a shortcut mode where the pre-processing was affecting the information. So we discussed the pre-processing, we changed it, and we reran those silencing maps. You can see here now the silencing map looks much more reliable. It's not looking, it's looking more at the tumor and looking less at those borders. And more than that, is also it also improved its accuracy. So this was one of those moments where I realized explainable AI is not only needed at the time was it would be nice to understand what a model learns, for sure. We are scientists, right? But more than that, it's all about patient safety. We want systems to be reliable. We want systems to operate under different conditions, right? And we don't want systems to sort of cheat on us in the way they are solving problems. So we've been also working on elucidating those patterns. What you see here on the left, this is a combinations of systems that are trained on different setups. So this test on variable that's moving now the animation. And then on the vertical axis, you see how the systems were trained. Now, typically what we know from the theory is if the domain you train matches the domain you test on, then you have the best performance, which is more or less reflected by that sort of, if I can draw here, this diagonal line here between test and train, right? When we move offset from this diagonal line, we are introducing perturbations. Here in this case, perturbations were simple contrast. And we were asking the question, how do the silencing maps change as a function of performance? So now the red colors indicate high performance in segmenting gray matter in this case. And blue means a low performance, red means a high performance. And then on the right, you see how the attention of the neural network, here a unit, changes as a function of this interplay between train domain and test domain. So here's where we are now using those gradients as a fingerprint of quality control. And in the last year, we've been investigating how those fingerprints can be used for several applications. So how do we actually know what the system is learning? So I already talked about those shortcuts. This is another example where the system is actually looking at snow to classify here the husky. But there could also be biases. But what if something is actually new knowledge? So this is the analogy to the AlphaGo system where there was this new move that the system actually came up with, and we humans, we learn now from that system. In medicine, I'm not aware of that paradigm where we're actually learning new things from an AI system. I hope we get there, but this is sort of the three, or maybe there are more scenarios where the system might be learning wrong patterns, but what if the system is learning the right patterns? And how do we humans, if we cannot even see those patterns, can validate those patterns for real use? So one way to maybe simplify here is to align, right? So when we align, basically we try the AI machine to resemble the patterns of functioning of a human, right? So here's where I want to highlight one study that is very interesting and where they actually trained three models. They trained this blue model, the white model, and the red model. The white model is a model where there was an alignment with the human. So you see here on the right, the humans provide some areas of attention, say AI, look at this area, right? And then the white model is basically your vanilla model where there's no guidance whatsoever. And then at the bottom, we see a red model. This is the opposite. Basically saying, do not look at what the humans do. Now, what is amazingly or even shocking is that the AUC of these three models is nearly the same. How come an AI model can perform the task, in this case, analyzing the lungs, without even looking at the lungs, right? So this comes with this set of questions about what is the system doing? Is this some kind of shortcut that might or might not generalize? And how do we actually evaluate that quality of alignment. So we've been working on those questions of there has to be a catch. There has to be a trade-off between alignment, human AI alignment, and different dimensions. And I want to show you briefly one result. Here is a study where we are actually aligning. And here we see that on the right, we were actually aligning models, and then we were analyzing how this amount of alignment, no pun intended, aligns with metrics in fairness. So for the sake of time here, what we have found so far is that alignment helps, but it should be graduated. And you can see that as we actually increase that alignment, we improve the situation. But there's always a trade-off with the amount of alignment that we have. And so on. I want to then maybe jump to some of the latest work on XAI, where I think many of us, we are aware of language. And this is where we are actually now. In XAI, the frontiers is how do we actually deal with that really larger black box where we want to be multimodal, where we want to be longitudinal, and we have an improved communication of explanations of explainable AI through LLM technologies. Thank you very much.